Hello, ma'am. Yeah, so I guess I'm audible and everything is fine. We will just start in 2, 3 more minutes. Hello, ma'am. Yeah, so I guess I'm audible and everything is fine. We will just start in 2, 3 more minutes. Hello, ma'am. Yeah, so I guess I'm audible and everything is fine. We will just start in 2, 3 more minutes. Okay, so I'll start the recording and I'll ask after that the Anvesha representatives to start.
Yeah, good afternoon, everyone. We welcome you to the 2020 Abel Prize Talk, which is organized by Anvesha and Club of Mathematics, IISER Thiruvananthapuram. And I would like to welcome all the audience and the speaker, Dr. Nikita Agarwal from IISER Bhopal for the talk. And this year's Anvesha is proud to be sponsored by Shabari Scientific Supplies and Apparatus. And I request Sadhika from the CMIT Club to introduce the speaker and welcome the speaker to the talk.
Thank you, Ravikar, for speaking on behalf of Anvesha. So, hello everyone. This is Sagnik, and I welcome you all on behalf of CMIT to the 2020 Abel Prize Talk organized by the Club of Mathematics in association with Anvesha as a part of the series of talks for the annual Science Fest of IISER Trivandrum. The Abel Prize, named after Norwegian mathematician Abel, is one of the most prestigious awards in mathematics given every year to one or more outstanding mathematicians. The 2020 Abel Prize was jointly awarded to Furstenberg and Margulis on March of 18th. They were cited for pioneering the use of methods from probability and dynamics in group theory, number theory, and combinatorics. Among other things, they invented random walk techniques to investigate the structure of linear groups. A common thread in the work of both the mathematicians has been the use of techniques from ergodic theory, which typically studies chaotic systems that evolve in time, eventually exploring various contexts. We are glad to have today with us Dr. Nikita Agarwal, a faculty at the department, providing us with an expert exposition on the research and significance behind this year's Abel Prize. She completed her PhD in mathematics from the University of Houston, Texas, in areas related to dynamics of cell networks and joined IISER Bhopal in 2011. Her primary research interests lie in pure and applied dynamical systems and ergodic theory, and she has been working on several projects related to dynamical systems. Dr. Agarwal is also an instrumental part of the Committee of Indian Women in Mathematics and the worldwide May 12 events. We are looking forward to an exciting session this evening, and I welcome the speaker on behalf of all the participants and the club. For the participants, do put your questions and comments in the chat section or unmute your mic at the end of the talk to interact with the speaker. So I'll tell Dr. Agarwal to take over from here. Thank you.
Okay, thank you very much. I will share my screen now. So just let me know if you can share, if you can see my screen.
Yeah, it's visible.
Okay. So good afternoon all. I thank the Club of Mathematics and Science Club Anvesha of IISER TVM to organize, first of all, such a lecture series and also organize this talk. It was also a learning opportunity for me because the works of these two mathematicians who are recipients of this award for this year is so vast that it's difficult for anybody to assimilate everything that they have done. So it was surely something. I also learned something in the process. So a quick disclaimer: this talk is, of course, cannot do justice to everything that they have worked on. So I'm going to present a few works of theirs, and I have chosen them and I have chosen the content so that it's accessible somewhat to this audience. So we can, of course, take up questions towards the end about this presentation or something else you want to talk about. And also, the organizers had asked me to speak about Indian women and mathematics towards the end. So I'll do that after we are done with questions on the talk. So I'll take a few minutes about talking about IWM. Okay. So let me first begin by talking about the prize. As just mentioned, it was established by the Norwegian government in 2002 on the occasion of the 200th birthday of Niels Abel. And this prize recognizes contributions to the field of mathematics that are of extraordinary depth and influence. And there's a cash prize of 7.5 million Norwegian krone. And since 2003, it has been awarded annually. So a little bit about Abel. He was born in 1802 and he died quite young, but he made pioneering contributions. So one of the things that I would like to highlight here is he gave the first proof of what is called the general binomial theorem. So all of you are aware of binomial theorem. So if you look at the left-hand side here, x plus y to the n, where n is an integer, you know the expansion, right? You know the binomial expansion. But this one looks a bit different. There is this z that you can see here. So if z is 0, then it's just the usual expansion, binomial expansion. But this is called the general binomial theorem and it's attributed to Abel. So of course, this is just one thing that I thought might interest you because it's not commonly talked about, this particular expression. So, so yeah, if you can see this picture on the top, this is the medal. It looks like this. And let me now come to the list of prize laureates from 2003 onwards. So this is the list, and you will see that a lot of these names are, of course, there are books written by them. You know them. Sometimes some of these names from even school time. So example, you can see Andrew Wiles, you can see John Nash, and so on. So I'll not go over this list. Of course, each of these laureates are marvels in their own rights, and their works are so extensive that, of course, one cannot talk about all of them. So we will focus on this year's prize laureates. So, which is so it was given to Hillel, Furstenberg, and Gregory, Margulis. So, this picture that you see on the screen has been taken from Abel Prize website. So, I have just taken it from there. But let me read out what the chair of the committee had to say. The works of Furstenberg and Margulis have demonstrated the effectiveness of crossing boundaries between separate mathematical disciplines and brought down the traditional wall between pure and applied mathematics. And a glimpse of this you will see in this talk. Okay. So let me first begin by giving a brief biography of Furstenberg. He was born in Berlin in 1935 in a Jewish family, and just before the Second World War, his family moved to the US. And specifically, they were based in New York, where he obtained his schooling, high school, college. He obtained his bachelor's and master's in 1955. And you can see that he published 2 papers in American Math Monthly during his as a student. And I'll just read out the titles of these papers: Note on one type of intermediate form and on the infinitive of primes. So then he obtained his PhD in 1958 from Princeton University with Solomon Bochner. He was an instructor each at Princeton and MIT for a year before moving to Minnesota, where he was an assistant professor in 1961. And he was also promoted to professor there. But he decided in 1965 to move to Hebrew University. And he was there till his retirement in 2003. He has received several awards and prizes. Among them are Israel Prize, which is a top honor in Israel, Wolf Prize in Mathematics. He is a member of the Israel Academy and the American Academy of Arts and Science. And this is, you can see Furstenberg's picture on the right. Okay. So now a short biography of Gregory Margulis. He was born in Moscow in 1946. He won a silver medal at IMO at the age of 16. Obtained his PhD in 1970 from Moscow State University with Yakov Sinai, who is also an Abel Prize laureate, 2014. And this is quite interesting, that due to discrimination for being a Jewish, he did not get a job at Moscow University. So he worked at a less prestigious institute, which is called Institute for Problems in Information Transmission. So I put an asterisk here because I wanted to remind myself of saying something at this point, which is that this association, even though it was not his first choice, but it resulted in a work which I'll talk about in this presentation. And it turned out to be a path-breaking work. And it was because of the environment, because of the colleagues and the expertise that he could get in this institute. So I'll talk about that. He is also a Fields Medalist, which he received in 1978 for his work on lattices in Lie groups. And then he moved to Yale in 1991. He was elected to the US National Academy of Science in 2001 and is a recipient of the Lobachevsky Prize and the Wolf Prize. Okay, so this was about their biography. I will mention one more thing about Furstenberg, that when he published his early papers, people felt that it was not by one single person, but Furstenberg is being used as a pseudonym for a group of mathematicians, because the techniques that he used were quite vast, and the work was so deep. So this is something that I found when I was researching for this talk. So I just want to check if I'm audible and you can see my screen.
Yeah, ma'am, total.
Okay. Okay, so now let us move on to their works. So as I said in the beginning, I have picked up a few of the areas in which they worked on, and which were recognized by the committee which awarded this prize. So the first one is their um, um, contributions to number theory. Okay. So I found out that there was a talk by Professor Srihari Sridharan some time ago, which was organized by, I think, the Club of Mathematics um, on arbitrary long APs. So I probably will not spend too much time on this, but it's an important work that Furstenberg was involved in. Okay, so there is this concept of a positive upper density for a subset of integers. Okay, so integers are 0, plus minus 1, plus minus 2, and so on. Okay, so how do you define this positive upper density? You look at the set A and you see how many points in A lie in the interval minus n to n. Of course, we are only focusing on integers. So you can see that there are 2n points, and I'm seeing how many of these points are in A. I look at, so this vertical lines represent the number of points, and you divide by 2n plus 1. So this is kind of the average number of points in this interval, and you take lim sup. Okay, so it's a good exercise to find out set A for which limit does really lim sup is what you're looking at. Okay, so this number, this limit, superior, if it is positive, then you say that this subset A is positive upper density. Okay. So a few examples. The set of odd numbers has upper density, half. Right? So half of these points will be odd, and it should be half. N is 0, right? Because at one cutoff, you will not add more points to the numerator. And the set of primes has density 0. So this is kind of very interesting. So that means primes are in some really sparse Z. Okay. So in 1936, Eros and Turan conjectured the following. Let A be a subset of integers with positive upper density. Then for any n greater than or equal to 1, A contains an arithmetic progression of length n. So all of you must be aware of what arithmetic progression is, but it's just a sequence of numbers which are separated by a fixed length. So one sees them as A plus D, A plus 2D, A plus 3D, and so on. Right? So A is the starting point and D is the common difference. Okay. So what they said was that a positive upper density subset of integers has arbitrarily long arithmetic progressions, because for any n you can find a progression. Okay. Now, this conjecture was proved by Semeredi in 1975 using combinatorial arguments. And Semeredi is an Abel Prize winner, and he got it in 2012. In 1977, Furstenberg gave another proof of this conjecture by Eros and Turan using ergodic theory. And he gave this proof using what is called now as Furstenberg's multiple recurrence theorem. So this recurrence is an important concept in dynamics, and I'll come to this when I talk about in due course. So he used this idea of multiple recurrence to actually give a proof of this conjecture, which was at that time not a conjecture because it was already proved, but using other techniques. Okay. So in 2008, Furstenberg's work inspired Green and Terence Tao to prove the following. The primes contain arbitrarily long arithmetic progressions. So now you have to watch out for the difference between this statement and the original conjecture. So conjecture was for positive upper density sets, right? But we know that primes have zero density. So therefore, this is something else, right? The statement is not contained in the original conjecture, right? But primes give an example of a set which has zero upper density, but it still contains arbitrarily long arithmetic progressions. Okay. So this is Furstenberg's contribution to number theory. And now let us talk about Margulis' contribution to number theory. And it is specifically to a conjecture which is called Oppenheim's conjecture. So in 1884, Meyer said the following. So let Q be an indefinite quadratic form in 5 or more variables over the rational numbers. So coefficients are rational numbers. If Qx is 0, has a non-zero real solution, meaning that if this quadratic form has a real solution, real 0, then it also has a non-zero integer solution. Okay. Now this fails to hold when you have 4 quadratic form in 4 variables. So the above result is a strict result in the sense of number of variables. So this is one example of a quadratic form in 4 variables which does not satisfy this property. And it's not difficult to prove this. So I'm not going into the proof, but it uses elementary techniques from number theory to show that this does not have this property. Okay. Now, in 1929, Oppenheim conjectured the following. So let Q be a real, non-degenerated, indefinite quadratic form in 3 or more variables. So non-degenerated means that you can't reduce the number of variables, roughly. Indefinite means that it doesn't become 0 at any point. Okay. So at any non-zero point, I meant. Okay. So suppose Q is not a multiple of a form with rational coefficients. So this statement is just hinting that you are not in the Myers case. Okay. So Q is not a multiple of a form with rational coefficients. Then for any epsilon greater than 0, there exists a non-zero rational vector x such that mod of Qx is less than epsilon. So you don't have a 0, but you have almost a 0. That's what it's saying. That you have a rational vector which is not a 0 probably, but it's almost a 0 because it's as small as you want. Right? For any epsilon, there is a rational vector such that this happens. So you can think of epsilon to be really small so that you still have a non-zero rational vector such that when you evaluate Q at that rational vector, you get in modulus less than epsilon. Okay. So this was Oppenheim's conjecture. And again, it is strict in the number of variables. That is, it fails to hold if you have a quadratic form in 2 variables. And this is the example where alpha is an algebraic number which is a solution of a quadratic equation with integer coefficients. Now, in 1987, so after almost 60 years, Margulis proved this conjecture, and he used methods from ergodic theory to prove Oppenheim's conjecture. Okay, and M.S. Raghunathan related this conjecture to for the case when the number of variables is 3 with a problem on lattices, and it was also known that it is enough to prove this conjecture for 3 variables. Okay, so M.S. Raghunathan also has played a significant role in Margulis's approach to solve this problem. And later on, Margulis and S.G. Dani, they improved this result. Okay, so there is contribution from India towards this Oppenheim conjecture and its generalizations and improvements. Okay. So now this was about number theory. Of course, as I said, this was not everything that they worked on, but this was sort of, possible for me to put it on the slides and make it accessible. So let me now move on to their contribution in probability theory. So random walks. So what is a random walk? It's an important branch of probability theory, and it's a path consisting of a sequence of random steps. So random steps roughly refers to you don't have a definitive path. So you can see this picture on the right, which I have borrowed from the internet, where a drunkard is walking around this lamppost on a street which is you can think of it as a slope. So the question is that will he ever reach the lamppost, or will he slide off the road? So you can see that he's taking these random steps, right? So that's what I mean by randomness. So Furstenberg and Margulis invented random walk techniques to analyze mathematical objects such as groups and graphs. And that's where this idea of recurrence, which I talked about early on, comes in. So Poincaré at the end of 19th century proved that under certain conditions, any orbit in a dynamical system will return or come close to any point in the space. Okay. Now, what is a dynamical system? Any system that evolves with time. Right? So you can think of motion of a particle in the space and so on. So this idea is called recurrence. And random walk technique can be used to connect recurrence with the size of the group. You will see that in a minute. If the group is too large, it is likely that no recurrence will occur during the random walk and vice versa. Okay. So what Furstenberg and Margulis did was they designed random walks technique to predict the size of the group. Okay. And if they found out that if the size of the group is too large, then recurrence it's probably will not occur. Recurrence will probably not occur in that space. So they introduced probabilistic methods to solve many open problems in group theory, number theory, combinatorics, and graph theory. So let me describe random walk in Zn. So what is Zn? And I'm going to focus on n equal to 1, 2, and 3. So when you look at n equal to 1, you are in Z. So you have the real axis, real line, and you have these integers. So you can think of it as 0, 1, 2, and -1, -2, and so on. When n is 2, you have an integer lattice. So this is just the x and the y axis where you have 0, 1, 2, and so on. In the y-axis, you have 0, 1, 2, and so on. And this is how you have. And similarly, in n equal to 3 case, you think of R3 and you just pick points where all three entries or all three components are integers. Okay, so that's an integer grid that you see in Z3. So I'm going to consider the following process where, suppose if I am at 0, I can move to +1 or -1 with probability half. Okay, so moving from 0 to +1 has probability half, and moving from 0 to -1 has probability half. In general, from any integer point, probability of moving to the right neighbor, so these are called neighbors. The next integer will be called a neighbor. So moving to the right neighbor is half and moving to the left neighbor is also half. Now when you come to Z2, you have 4 neighbors. Okay, along north, south, east and west. And in all the 4 directions, probability is equal, which is 1/4. In Z3, you have 6 directions, and in each direction, you have probability 1/6. Okay. Now I want to ask the following question. Starting at the point 0, let Pn denotes the probability of reaching the point 0 in exactly n steps. Okay, so I want to ask this question that if I start at 0, will I ever return to 0 following this random walk? Okay. Now, when you can immediately see that if you start at 0 and when you come back at 0, you have to come back in even number of steps because you want to come back to 0. So if you take a right step, you have to also take a left step to counter it, right? So in some sense, the positive steps have to cancel the negative steps. So therefore, P at any odd number is 0. Okay. Now let us compute P of 2n, meaning you're coming back to 0 in 2n steps. Now, very simple argument from probability theory will tell you the following. So out of these 2n steps, exactly n steps will be in positive direction and remaining will be in the negative direction. And hence P2n will be 2n choose n, which is you're choosing n steps, which are, let's say, in the positive direction, and obviously the remaining will be in the negative direction. Half, which is the probability of moving to the right to the power n, and half to the n. So it's like a binomial experiment, right? Which gives you this. Now you can use Stirling's formula to get that P2n looks like 1/√pi times n when n is large. Okay. So if you summation over n, P2n, it will diverge, right? Because you have this series looks like 1/√n. So it diverges. So from probability theory, one knows that if this summation diverges, this summation is nothing but the expectation of the number of times you will visit 0. Number of times you will return to 0. So this is the expected value. So it's known from probability theory that if this number diverges, this summation diverges, then we are sure to return to 0 infinitely many times, meaning the probability that you will come back to 0 infinitely many times is equal to 1. If the expectation, this number, this series is divergent. Okay. So in Z, if you have equal probability of moving to the right or the left, then sure you will come back to 0. And this is not the case if the probability is unequal of moving to the right and to the left. Okay. In that case, it's not true. So I'm not going into those details. Now let us come to random walk in Z2 and Z3. So if you start at the point 0, let Pn denotes the probability of return in exactly n steps. In Z2 again, in 2 dimensions again, you can quickly check that you can't come back in odd number of steps. So probability of coming back in 2n plus 1 number of steps is 0. So I would like to make a technical point here, that when I say that probability Pn denotes the probability of return in exactly n steps, it's like a conditional probability that you're coming back to 0 in n steps given that you started at 0. So it's not it's actually a conditional probability that we are talking about, but you don't have to worry about too many technical details as long as you understand the gist of it. So you can't come back in odd number of steps. So in this case, what happens is P2n turns out to be square of whatever you got in the Z case, because now there are two directions in some sense. And it looks like 1 by pi to pi n when n is large, and therefore again the summation diverges, and in this case also we are sure to return to 0 infinitely many times. Okay. Now coming to Z3, when you have an additional direction, it looks like 1 by pi n to the power 3 by 2. And now this series converges. Okay. And again, from probability theory, one knows that if this series converge, this means that we cannot be sure that we will return to 0. In fact, in this particular case, the probability of returning can be computing to approximately 0.3405 as opposed to 1 in the case of Z and Z2. Okay. So, and it will become worse as n increases, right, for Zn. Okay. So, so this was just an idea of the concepts of recurrence and random walks. But of course, this did not reflect their work. But I just wanted to highlight the problems that are there when one introduces randomness and so on. Okay. So let me now come to their contribution to graph theory. And this is the work that refers to that star in the biography of Margulis, where he was not given a job at Moscow University and he was working at some other place. And I said that he did some path-breaking work there. So let me talk about this work. So let us talk about what a graph is. So an undirected graph consists of nodes and edges between nodes. So by undirected, I mean that there is no direction. If you have an edge, you can go from one vertex to another in any direction. Okay. Of course, these. So I'm looking at vertices, which are the sides which are corresponding to an edge. Okay. So every edge corresponds to two nodes or vertices. Now, for a graph, there is an important quantity which is called an adjacency matrix. So for a graph with n labeled nodes v1 through vn, its adjacency matrix is symmetric, meaning that its matrix is same as its transpose, and it's given by A equal to Aij, where Aij, I'm sorry, this should be little Aij, where Aij is 1 if there is an edge between Vi and Vj, and it's 0 otherwise. Now, since A is symmetric, we know by spectral theorem for symmetric matrices that it has eigenvalues, real, which are lambda 1 greater than or equal to so on up till lambda n. And these eigenvalues actually say a lot about the properties of the graph. I'm not going to go into that, but it's something very important in graph theory. If the graph is k-regular, meaning that each vertex has exactly k edges connected to it, then lambda 1 is equal to k, meaning the largest eigenvalue is actually k, and the least eigenvalue is greater than or equal to minus k. And moreover, if you have a k-regular graph, then the sum of eigenvalues is 0, and the sum of squares of the eigenvalues is n times k, where n is the number of nodes and k is the degree. Degree meaning the number of edges which are connected to each vertex. Now, let me define what is called an expander graph. So let G equal to V and E be a graph. So V is the set of vertices and E is the set of edges. And let A be a non-empty subset of nodes of G. Okay, so I'm looking at a subset of V. So let E, A, A complement be the set of edges between vertices in A and its complement. So you imagine a graph, you take a graph, subgraph, which has a subset of vertices. Now you see how many edges are going out from this subgraph. So that is your EAAC. So this expansion constant, which is also called Shiger constant, is denoted by Hg, and it's defined as minimum over all subsets of the vertex set, ratio of the number of edges which go out from A divided by the number of vertices in A. So this mod A represents the number of vertices in A or number of nodes in A. So what is this ratio? It represents the average number of neighbors in the complement of A. Now, there is an easy exercise that a graph is connected if and only if the Shiger constant or expansion constant is positive. So what is connected a graph? It's a graph where there is a sequence of edges between every pair of nodes. So you can go from any node to any other node via a sequence of edges. So a k-regular graph G with expansion constant greater than or equal to epsilon, where epsilon is a positive number, that means a k-regular graph which is connected and whose expansion constant is greater than or equal to this number epsilon, is known as k epsilon expander. Okay. So k is the regularity of the graph, meaning the number of edges connected to each node, and epsilon stands for the minimum expansion constant. Okay. And you can immediately see that mod, the number of elements in the edges from A to A complement, is less than or equal to k times mod of A. Why? Because roughly every vertex in A has k neighbors. So it's possible that from a vertex which is in A, you can have all the k edges which are going outside in the complement. Therefore, to every vertex in A, you have k neighbors. Therefore, the number of edges would be at most k times mod A. Of course, this is hard to be satisfied for every A, but this is nevertheless an upper bound that we need. Okay, so this means that this Shiger constant is bounded above by k, because for every A, this number divided by mod A is less than or equal to k. So therefore, the minimum will also satisfy. Okay. So this is an example. I'll come back to this example. So right now it looks intimidating, but it's an example where you have 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices, and it's an expander graph. Okay, and it's one of the graphs that was constructed by Margulis, and I'll also talk about the construction in a minute. So I'll go over the definition of what is called an expander family. So right now we define an expander graph, right? Now we will define expander family. So let Gn which is Vn, En, be a family of non-empty connected graphs. It is called an expander family if there exists a V and a H such that mod of Vn goes to infinity, meaning that these graphs are such that as n goes to infinity, the number of vertices become infinite. Every node in each graph has at most V neighbors. Okay. So this means what? This means that if you look at any vertex in any graph in the family, it can have at most V edges that are going out. And this is sometimes known as sparsity because this is controlling the number of edges out, a number of degree of each vertex. Right? V is the upper bound on the number of neighbors any vertex can have. Finally, each graph has expansion constant at least h, meaning that the Cheeger constant is at least h. This means that you're also controlling connectivity. On one hand, you don't have a lot of neighbors. On the other hand, you have some connectivity, which is bounded below for every graph in the collection. So it is easy to find examples of expander graphs, but it's not easy to find example of an expander family. Okay. So you know the definition of an expander graph, K epsilon expander graph. You can immediately construct an example of a graph which is K epsilon expander for any K and epsilon. But the problem is when you have to construct a family, and that's where Margulis gave a family in 1973, and soon after his work, there was an outburst of examples, lots of examples of expander families. But his was the first example, and it's very easy to understand at least, but it's difficult to prove that it's an expander family. So let me explain this example. So just recall that Zn is the group with elements 0 through n minus 1 with operation as addition modulo n, meaning that you add two numbers and then you take mod n. So let's say if you add, if n is 4 and you add 2 plus 3, then 2 plus 3 is 5, and then you do mod 4, which gives you 1. Okay, so you are aware of this this group Zn. Now I define this Gn as the following graph. Its vertex set is the direct product of Zn with Zn. So these are tuples, right? And Zn with Zn and mod Vn, how many elements are there in the vertex set? N for this and n for this, so n square. Now what are the edges in Gn? Each a comma b in Vn is connected to these 4 vertices, okay, with addition modulo n. So I just explained what addition modulo n is. So a plus 2b, you find out the value, you take mod n. You look at b, b is anyway less than n, so it's okay. And so on. And their inverses. So you connect AB to all these vertices and also inverses of these. Okay, there is an inverse for every element. So how many edges are there connected to each vertex? There are exactly 8 edges which are connected to each vertex. They are precisely these and their inverses, right? Now Margulis proved that the family Gn is an expander family with lower bound on Cheeger constant h as 0.46 and v equal to 8. So v equal to 8 is not an issue because it comes from the construction. In fact, each vertex in the graph has exactly 8 neighbors for n greater than or equal to 3. Okay. And this uses, so there are 9 vertices. Each vertex is connected to 8 other vertices, right? Of course, you can see self loops. There are loops coming back to itself. And on some nodes, you have 2 loops, meaning that those 4 images, 4 vectors that I wrote down and the inverses, many of them are equal. So therefore, you have more than one edge that is coming back. So this is for Z3 cross Z3. Of course, when your n increasing, the number of vertices increasing, and it becomes more complex. So this was something that I could draw. It is using Mathematica. So yeah, this is an example of an expander graph which comes from Margulis's construction. Okay, so I hope I was able to convey some of the contributions of these two mathematicians, and I will stop here. A few references. I mostly use Abel Prize website, which is given here for a lot of content, and also the internet. And recently, actually 2-3 days back, I came across this announcement by Gujarat University, organize an e-talk by Furstenberg on November 5th. And you can register online if you are interested in attending this talk. So I will stop here, and I welcome any questions that you may have.
Thank you, ma'am. I guess I have to admit how wonderfully the talk was presented, and I guess all the audience will also admit the same about starting from the details from both Furstenberg and Margulis to the extreme details of their work. So at this point, we would ask from the audience if there are any questions or comments. They can unmute and ask the speaker.
So I have stopped sharing my screen, but I can do it again if it's required.
Yeah.
Yes, Sagnik, just a minute. I'm sorry, Sagnik, point well said. So 2019 was the first time the award was given to a women mathematician. Yes, so Karen. Yes, I'm sorry. There was some question, I think.
So there is a question from Ananta Krishna. He asks, expander graphs are basically those wherein the Cheeger constant is bounded both above and below. Is that right?
Yes, in some sense, because when you look at, so you have an upper bound on the number of vertices that can go out, right, which is V. So yes, so bounded below is anyway coming from the definition, and bounded above comes from the upper bound it comes from sparsity. Yes.
So this constant is an indicator of how sparsely the graph is connected.
Yes.
So I had one thing that could you explain a bit again how the Cheeger constant is directly related to connectedness?
Okay. So suppose what I said was that if your graph is connected if and only if Cheeger constant is positive, right? So
yes.
So now you can see that if Cheeger constant is positive, then it's not difficult to prove that the graph is connected. Why? Because Cheeger constant being positive means that minimum of that ratio is equal to something positive, right? That means for every A, that ratio is bigger than that number. It's positive, right? So that means
So that ratio is just the ratio between the number of edges going out and the total number of vertices.
Yes, and the total number of vertices in the subset in A.
Yes.
Right. So that means, let's say if I look at one vertex, if A consists of a single vertex, then you are saying that you can go out of that vertex, right? And you know the minimum number of edges that will go out from that vertex, because Cheeger constant is telling you, right? If minimum is equal to some number, then every ratio will be greater than or equal to that number, right?
Okay.
So using that, you can show that you can go from any vertex to any other vertex via a sequence of paths by building these sets A. You start with a single vertex, you find a neighbor using Cheeger constant. Then you take that vertex and the neighbor as the set A. You will find another neighbor outside using Cheeger constant being positive. So this way, you can expand your set A so that you find a path which connects any vertex to any other vertex.
Okay. Yeah.
Okay, so
That makes sense.
so yeah, it's kind of a constructive proof that you start with a single vertex and then you keep on expanding, and you will be able to fill the entire vertex set because A is arbitrary, right? A is any subset of vertex set.
Yes.
So we are looking.
So there is a comment that we are looking at the ratio of connections between the graph and its complement to the number of vertices, and look at the minimum of this.
Yes. Yes, absolutely.
Yeah. So another question is, in case of Oppenheim's conjecture, could you explain why indefiniteness is required?
Okay, so see what, so I think it is required to, so you want to come from a non-zero real solution to, I'm sorry, you want to come from, you're talking about Oppenheim's conjecture, right? So,
Yeah.
So in Oppenheim conjecture, you are going to construct a rational vector, right? So there are some, so if you don't take indefiniteness and you have a point which is kind of a singular point, which is non-zero, and you have the solution becomes zero, then this you will be able to construct some sequence of rational vectors which will kind of diverge. So these points, which are singular points where the quadratic forms become zero, will cause problems in will kind of contradict this eventual conclusion. Yeah, it's difficult to explain it in full details here, but it's kind of poses problems in finding out a non-zero rational vector which is in modulus such that mod of qx is bounded above by epsilon.
Okay. So is there any other questions or comments from anyone else? Okay, I don't think there is anything else.
So, Saknik, if I can take a few minutes to talk about IWM, that is okay.
Yeah, sure.
Excuse me. If you're done with all the questions, let us just unmute ourselves and thank the speaker.
Yeah.
Thank you very much, ma'am. Now you can continue.
Okay, so as was mentioned earlier, I'm associated with Indian Women and Mathematics, which is a collective of Indian mathematicians to encourage and promote more women to pursue mathematics. And we also organize a lot of activities throughout the year in this regard, and many of these activities are not just for women students, they're also for everybody who is interested in maths. So one of the activities is mathematical workshop for young women, which was actually organized at IISER TVM last year in December. which was the first such workshop that we organized, which was a long-term activity in the sense that it was for a longer duration and there were hands-on training, tutorials, and so on. So other
Yeah,
than
I
that,
guess Dr.
yeah.
Srilakshmi was associated with that event too. She is also
Yes.
in the meet.
Yes. Okay. So, and the other activities that we organize are regional workshops and then visitors program where we invite visitors from abroad as well as from India to basically go to remote locations uh, in in the region of their interest, and we have covered actually all of India that way. And then we have an annual conference that happens every year. So, because of COVID, we were not able to organize, we had to cancel all the events for this year. And we are holding some visitor talks online, and two of the talks have already happened in the last 2 months. And this month, the talk is going to be on 30th of October. And if you're interested in that, I'll send a link to Satnik and he can pass on to the other. So let me use this chat window. Let me copy the IWM website. If you're interested, you can go over it. And this initiative is funded by National Board for Higher Mathematics, NBHM, and also by Committee for Women in Mathematics, which is International Math Union. So we are also connected to other math associations and organizations globally. And May 12 is, so that's how we also got involved in the May 12 initiative. So there was um, uh, an event that was organized by Math Club also, right? This year. So that was something that
Yes.
I got to know, and we are going to highlight your activity on our IWM website soon, along with other activities that happened in India under Math 12 initiative. So yes, if anybody wants to ask me something about IWM or anything else, I'll be happy to share information. That's all.
Thank you, ma'am. So anyone else has anything to say? So if not, then let's thank the speaker again. And we are very glad to have her here today. And we hope that in future, when things are normal, maybe she can visit the institute also for future events as well. So thank you everyone for attending, and thank you, Dr. Agarwal, for the talk. I guess we can leave now. Thanks.
Thanks, Sapna. Thanks, everyone.